So we have completed like what, 3 sessions. So we are now on 5th session, and in this session mostly we'll like discuss about the thermodynamics part. And yeah, the same as usual. I'll derive the equations which in an easy manner for you to be able to understand, and what are the derivations that hasn't been derived, right? So, and also in between those topics, and also I will discuss few questions. So that's how we have been discussing, and that's how we will do today also. So beginning with the introduction to thermodynamics, mostly the metallurgical thermodynamics, not the mechanical or chemical department's thermodynamics. So whatever we are going to see here is mostly related to the metallurgical thermodynamics, right? You will see solutions, just like in last week 5, you have seen the solution thermodynamics, right? It is mostly related to chemical and metallurgical thermodynamics. So let's start with basics. Basics is same for any type of any departmental thermodynamics, right? You have first law, second law, and third law. So first law gives you the energy conversion, right? The energy and work conversion. This is what will be written, the first law of thermodynamics, right? And because there is a conversion, now you need to, if you want to remove that conversion thing, then you need to add one constant. So you need to add one term, and that is, this is our energy, heat energy, and the term will be our internal energy, and this will be our work. And work can be any type of work, either it is a PdV work, or it is an electrochemical work, or any type of work, right? So this is our first law of thermodynamics. Then the second law. Now what does the second law tell us? Second law tells us that some part of energy is being lost, or some part of energy is not being retrieved, right? So, and how do you define that? And people have tried to define it by doing experiments at constant temperature, right? So if I do something, for example, if I do gas expansion, right? So some part of energy is being lost and at a certain temperature, and they have this relation when you do the reversible process. We are not talking about a reversible process. So you can only relate entropy to energy. The reversible work should be del Q by T. This relation is only possible when you do the reversible thing, right? If you do the reversible, then again there is some thing of entropy that is again coming into picture. That is irreversible. So that is what the second law says. And you have a third law. See, third law is basically defining a reference scale to the entropy, right? So people have seen, yeah, people defined the energy and work conversion. Yes, that's good. And what's next? After that, people have seen that some part of energy is being lost, and we do not know, some part of energy we are not able to retrieve. Right? So people have defined a term called entropy. And yeah, first law of thermodynamics doesn't tell you whether the reaction is spontaneous or not. Again, so it just tell you the conversion, but it doesn't tell you whether the reactions are spontaneous or non-spontaneous, right? And what is the directional, how they will the left hand reaction or right hand reaction. So that's how the second law came. And once the second law came, the people started asking, what is the reference scale? Yeah, you defined your variable entropy, then what is the reference scale for it? So then the reference scale came, the entropy of any substance at 0 Kelvin, right? Because entropy depends on temperature. So then at 0 Kelvin it is 0. So they defined the scale, but again there were many mishaps, right? So whenever you define something without knowing, there will be many things that comes into picture. And the first one is the crystallinity. The second one is the pureness, how pure the material is. The third one is it comes from spins. Okay. Now all these things came to how can you achieve entropy 0 if you have some impure materials, because there is a configuration entropy. Configuration entropy is nothing but how many ways you can distribute your system. So for example, if there are three atoms A, B, C. Now what do you mean configuration entropy? So it means their replacement can change. They can sit as B, A, C, or they can even sit as A, B, C, or C, B, A. Right? So it changes. Right? We cannot certainly define it. So there are how many ways? So three things, three places. Right? So 3 factorial. 3 times 2 times 1, which is 6. You can do it in 6 ways. Right? So there are 6 types. So system, it depends on system which arrangement it wants to take. So there goes the configuration entropy. So that's how people started asking questions like, how do you define them? Then Max Planck came and said that if your system is in internal equilibrium, what do you mean by internal equilibrium? Internal equilibrium, nothing but the system is like everything, the crystallinity is there. So wherever you find, you have the symmetry, and then you find your pure material, and the spins are also there, and the spin interactions are also having the lowest energy values. So then we can assume our system is in the internal equilibrium, which is not possible, but for fairness, they made this statement. So from there, at 0 degree Kelvin, our entropy is approaching to be 0 or maybe 0. It's just a theory again. So that's all about the thermodynamics part. The first law, second law, and third. Right? I don't need to explain the zeroth law, because zeroth law is nothing but what it tells you about the temperatures, equilibrium, where your equilibrium. Sorry, it tells about the equilibrium. For example, A and B are equilibrium, then B and C are equilibrium, all the bodies are equilibrium. Just tells you about equilibrium. That's all. Now, moving on to how to apply this thermodynamics part to nanomaterials. Right. So before that, we need to know what are the variables we can measure in thermodynamics. And the most after combining all these equations, the first law, second law, and third law, so we arrived to the free energy. Right. So G is our free energy, or the energy available to us. Now H is enthalpy, which is the total energy of the system. And this term, because again this is dependent on temperature, so we will probably T to get the energy. This is some part of energy that we couldn't retrieve, so that's why it is like this. Yeah, so this is the thing we want to know, because if it is negative, then we have energy with us and we can do anything. If it is positive, then we need to supply energy, because we cannot do it, cannot happen spontaneously. That's all. Now, again, is it easy to measure enthalpy? And is it easy to measure entropy? No, it's not easy. So then how do we make it easy? So engineering is all about how to make things simpler, so that we can measure, change, do things, so on and so forth. So the best thing is to do the differentiation, right? How the variables are changing with respect to each other. Then dH minus dt. So dg will be dH minus tds minus s dt. Now what is enthalpy? So enthalpy will be equals to internal energy plus P. Now if you do the differentiation of this guy, du plus pdv plus pdv. Right. And if you do enthalpy at constant pressure, it will be equal to the first law of thermodynamics. Right. So yeah. Then what is again from first law? If you do the differentiation, you will get dq du plus p dv. Right. Now we do not know du here, so we try to substitute this du here. So this is like equation 3, equation 4. This is equation 2, and this is 1. Okay. Now what I am trying to do is I am just jumbling with 3 and 4. Okay. So what will it result? dH will be equals to dq minus pdv, and there is plus pdv term plus pdv term. right? Now, and this dH will be equals to dq plus vd. Now from third law of thermodynamics we know, sorry, second law of thermodynamics, we know dq is equal to TdS plus Vd. Now this is equation 5. Now you substitute this guy here. dg will be equals to, what is TH? TdS plus Vd minus TdS minus SDT. So they both get cancelled. So dg will be equals to Vd2 minus SDT. Now you can see that we can measure the change in pressure. Right, all you need to have is some pressure gauge, right, to measure the pressure changes. And then here you have the temperature. All you need is a thermocouple to measure the temperature. So the parameters are dg is depending upon P and T. Right, that's all it says. Because C is a function of pressure and temperature. You can measure pressure and temperature because they are very easy to measure. Right. So that's how we arrive at this. Now, so whenever we write this equation, we didn't mention one thing, right, which is when do we apply this equation? So it's a question we always raise. If our system is closed, that means, for example, if you have a water, if you have any system, like if you have any phase, like phase alpha, right, and it is closed, there is no transfer of alpha from surrounding to system, right? Everything is closed. And here we can have a pressure gauge, right, which will tell you the pressure, and then we can have the thermometer, right? Pressure is measured here, temperature is measured here. You have PT relation. Now, so if it is applied for closed system, right? This is applied for closed system. Now what if there is an open system? Right. If we have open system, then there is a transfer of time. Right. Alpha can flow from here to here and alpha can flow from here to here. Then there is an addition and subtraction of this alpha phase. That's why we need another term, right? And that term is called chemical potential. Right. See, now we know how to write for open system. This is very rare, right? You see very few systems which are closed systems, but you will mostly see open systems, right? The boiling of water, the boiling of milk, and everything around you, the oxidation, reduction, whatever the type of reactions you are doing it in the presence of environment, right? There is nothing closed, or there is a controlled environment. For example, you want reducing atmosphere, you want hydrogen, or you want oxidizing atmosphere, you want oxygen, and you want to form chlorides for some metals, then you pass chlorine gas. So it depends on what type of environment you are creating. But there is open system, there is a transfer of mass or the transfer of species from system to environment, right? So that's the thing. How do you define that term? That term is defined as chemical potential, mu, and that is given by dg upon dni. Now what is my dni? dni is nothing but the moles of whatever the species that is being added to the system or subtracted from the system. Right. Now this tells me how the chemical potential is being changed. Now let me give an example. So free energy of say alpha phase is 50 kilojoules. It is per mole. Now what happens if I try to add 2 moles of alpha? G alpha will be 150 kilojoules. Right. So what do you say? Then my chemical potential will be equals to the change. How much is the change? 150 minus 50 will be 100 divided by how many moles are being changed? 3 minus 1. So let me write it again. 150 minus 50 divided by 3 minus 1, which is equals to 100 upon 250. So it gives me per mole. So actually the chemical potential, if you're talking in a pure phase, it is just free energy per mole, or free energy of the system per mole. That's what the chemical potential is. Now, for single systems, it may not be that much straightforward. So for example, if you have a single system, then that is straightforward. So you just divide it by number of moles, you will get your chemical potential. You will know how much energy is being changed whenever we add something. What happens if we have different species, right? 2 different species. Then there comes the thing called solution. So what do you mean by solution? Solution is made up of 2 parts. Solute plus solvent. Right. So you have a single system here. Then you add something, then it will become solution. So now you have a binary system. What do you mean by binary system? Binary system is nothing but I have 2 species, 2 different species. Or you can have 2 different phases. Right. So it is a binary system. Binary system is like 2 species, or you can have dual phase of still a single component. This is understandable. Steel, for example, iron and carbon, you have 2 different species. And what about the dual phase of a single component? Water and ice. Water is just a molecule of H2O. Ice still a molecule of H2O, but the different in phases is the density, right? And the crystallinity. Solid ice has crystallinity, but water doesn't have, right? These are 2 different phases, but a single component. Now, the question is, so for example, if I take a container, second, yeah. So if I have a container and it's filled with water, and then I have ice in it, right? So I have ice particles. Ice actually floats, right? Because it is less denser than water. So let's say we have mixed it and it is in a condition like this. Okay, for just a single instance. Now, so let's write the equation for it. What is the total energy of the system? G total will be number of moles of ice times the free energy of ice plus number of moles of liquid water or liquid times free energy of liquid water. Okay, so this is our total energy of the system. Now, what happens if I try to add? So there is N1. Now what happens if I try to add 1 mole of ice? Right. So if I try to add 1 mole of ice, then GT will be equals to Ni plus 1 Gi plus NL Gl. That's it, right? It's simple, right? Because all we need to do is add 1 mole. That's our final energy. Now, so everything looks simple. Now what happens if I try to add, let's say I have ethanol. See, this is my ethanol. And then I try to add ice. Or let's say for example water. I'm trying to add, you have ethanol plus water. So what I'm trying to do is, you will not define line, okay? Stay. Yeah. At first you have ethanol, then we are adding water in it. So this is now ethanol plus water. And this chemical potential is relatively a bit difficult topic to understand, but still I will try to maintain that decency level of understanding. Okay. So now it is a mixture of ethanol plus water. So what is the total free energy? Number of moles of ethanol into molar free energy of ethanol. Number of moles of water into molar free energy of water. Now, what if I have tried to add 1 mole of water into ethanol? Will it be same? Just simple? No, it will not be. Why? Because it shows a different deviation from the outside. Right? And the free energy is less. We have different free energy, which is not the same as this one. Just a simple addition. Right? No, it will not be. It will not be just that much straightforward, because the water molecules and ethanol molecules will interact. When there is an interaction, there is a change in energy. Simple as that. Then how do we define it? And we define it as rho g by the change in free energy with the change in number of moles. That is given as mu. So what was it for? Ethanol, right? So dGe by dLe into mu. And the same goes for water. Now this guy depends upon number of moles. Right. That's it. So this is how we define if there is some deviation, if there is some interaction between solute and solvent. Then we need to introduce our term called chemical potential. Right. And we'll come to that. How do we have a physical correlation? Right. Now, the next question is, mixtures. Right. So far we know this is our relation. Right. So del G equals to del H minus T del S. And again, there are simple things, right? If you know the del G, if you know del S, if you know T, then it is easy to find del H. That is not a big issue. Right? So all you need to find is, if I have an equation of 4 variables, all you need to do is find 3 variables, and the 4th variable will come out eventually. Now moving on to mixtures. So far we have seen the ethanol and water on mixing. Now how well they are mixing. Now what type of mixing we are seeing, right? And that mixing, either it is random, or there is an ordered, or there is a perfect stoichiometric. So how they are mixing, right? So for example, ethanol and H2O. So I have CH3OH and H2O. Right. Now, is H2O is being covered by H2O or ethanol? Right. So for example, now let's come to solid solutions, right? Because we are mostly talking about metallurgy, about solids, right? So let's come to solids. Now for example, if I have A atoms, A type of atoms, and it is FCC, right? So for example, A is an FCC, right? adding B, which is a solute, and B is my solvent. Okay, I'm adding a B into A, so I'm making an alloy of AB. Right now, so B atoms are added to A atom into A. So when you see in crystal structure, A atom will be covered by A, right? That is now. What happens if I add B atom? So what happens? Where the B atom will sit? Is it here? Is it here? Is it here? Or here? What is the probability? 1 by 4. Right? Then that is random. B can sit anywhere. Right? So it can sit here, it can sit here, it can sit here, it can sit here. What is the random solution? Right? Or B may not sit there. You can 1 by 5. You can have A and then you may have B. Who knows? It's a completely random solution. Right? So that's how. It's a random. Then ordered solutions. Ordered solutions, something what you will find the ordering. Right? There is no longer this very random type of state. Right? You will find the long range order or short range order. It depends what type of ordering you want to see there. And then you have perfect stoichiometry. That means like Al to O3. It's good oxides. Okay? Or you can take Na3Al intermetallic. So for every 3 Na atoms, you will have an Al atom. That's it. In ordering, you can see AB, 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 and so on. But you will have your order. And Na3Al, for every 3 Na atoms, you will have 1 N atom. Perfect stoichiometry. Right. In FCC itself, so for example, if in FCC you have corner atoms and face center atoms. So corner atoms will be taken by aluminum and the face center atoms will be taken by nickel. So effective is 4, right? So 3 plus 1, 4. FCC. Effective atoms. In FCC is 4. So 3 from face center, 1 from corner. That's right. Na3Al. Now, how do you get the relation? This is before mixing. Right? You have XA moles of A. Then you have XB moles of B. Right? So XA has XA moles of A and XB moles of B. Now when it is pure, the energy is constant. So that's why we got as Ga naught. And when B is pure, it has again constant energy, Gb naught. Now, what will the initial total energy before mixing? Total energy of A and B will be XA moles of G naught A plus XB moles of G naught. Right? Now, after mixing, what will happen? We will have G initial plus G mix. Right? So it's not as simple as that. Again, why? Because there is an interaction, and whenever there is an interaction, there is change in energy. This change may be negative, which lowers the final energy. Let's make it as G2. Okay? Final energy after mixing. This may be negative, which might lower this value, or this may be positive, which may increase the final free energy. And it depends upon interaction, what type of interaction we have. Okay? So now let's talk about random solutions. What do we mean by random solutions? Random solutions, again, the same. The probability of the atoms sitting next to each other will change. That's what we called from random solution, right? Now, so again, G will be equals to G initial, which is XA naught GA naught plus XV GB naught plus G mix. What is the change in energy because of interaction, right? And it can be from, it comes from two terms. One is the enthalpy. So how do you write G mix? The delta G mix, delta H minus T delta S. Right. Now what is delta H? It is mix and it is also mix. What is my delta H mix? Delta H mix is nothing but change in internal energy during mixing minus, plus the P delta V, change in volume during mixing. Right. Now come to delta X mix. One thing I have shown you, right? The configuration entropy. Yes. The thermal entropy. Right. So let's go. Let's write it here. Delta S mix will be equals to 1. The entropy coming from configuration. The entropy coming from thermal. The entropy coming from vibrations. The entropy coming from spins. So there are a lot of entropies. Right? Whenever you're talking about atoms, you have the configuration, how the atoms are distribution. The system needs some energy to distribute the atoms, right? So you need some energy to make students sit properly in a class, right? You have to shout, you have to do something. So the same, the system also needs some energy to configure itself, right? To arrange itself. And the next one is the thermal entropy. And because of whenever you have high amount of energy, then you have the entropy, right? The randomness. They're starting to move from here to there. And then you have my vibrational entropy. Vibrational entropy comes from when the atoms vibrates in that same place, right? And there is a spin interactions, and the spins may move up and down, right? When you increase the, for example, if you have a magnet and you put it in a furnace and you heat it above 500, 600, it loses its magnetism. Why? Because the spins will randomly arrange themselves. Again, the delta S for the spins. Right. Now, what we are seeing here, this will be 0, this will be 0, because it's not 0, but they are very low. You just neglect them. Right. And the same goes for thermal entropy. The only thing we are remained with now is configuration. Now, how do we do that? How do we come to that configuration? So, let's say, let's go with the simple property. Okay? Now, let's define our lattice. Okay, so, big. This is just a one-dimensional lattice, right? There is still the 3 dimensions. There is still the 3rd dimension. Right? It's only for simplicity. Now I have another one of A and B. Now how do we define my configuration entropy here? Right? So that is our question. Right? Now configuration is nothing but arrangement. Now let's arrange the atoms of A and B. So first, let's say, what is the probability of arranging A and B atoms? So First, let's define how many sites are there. Let's say I have NT sites. NT means total number of sites. NT is total number of sites. NA is nothing but number of A atoms. What is my NB? NB is nothing but number of B atoms. So for example, let's say it is a perfect system. We do not have any vacancies. Then that means every site is being occupied by A and B. So that means N total will be equals to NA plus NB. So there is no atom missing, there is no Frankel defect, there is no Schottky defect, there is no vacancies, there are no any other defects. Okay? So it is a perfect crystalline structure. Just assumption. So the total number of sites will be number of atoms of A plus number of atoms of B. Now, first let's arrange number of atoms of A. Okay. So then, what is the combination? So there are n number of sites. Right. So how do you do that? Nt factorial upon Na factorial. Right. That is what it is. Nt factorial. So write it. Yeah. So Nt P. What are the number of combinations? There are NT sites and you have N atoms, right? For example, you have 6 places and you have 3 students or 3 students. How many ways you can arrange them? That is 6p3, right? It's simple permutation. Same here. You have Na atoms and you have NT sites. How many ways you can arrange? NT P Ne. Right? Now, what is that? Nt factorial upon Nt minus Na factorial. And what is my Nt minus Na? It is Nt factorial upon Nb factorial. Right. Let me write it here. Nt P Na. Next. So the next question is, now all the atoms are same. Not all the atoms. So Na atoms are identical and Nb atoms are identical. Right? You cannot distinguish between aluminum atoms. Right? It is not possible. You can distinguish between isotopes, but you cannot distinguish between simple isotope. Right? So if you have only single isotope, then you can distinguish between atoms. That's why you have a relation. Then what happens? Then below here you will have Na factorial. That's it. And once my atoms are arranged, Na atoms are arranged, and there is no way for Nb atoms to be placed, right? So if I do that, even if I do that, see, Nt minus, I have Na atoms factorial upon Nb, that is Nt minus N factorial, which is Nb factorial upon Na factorial. Again, because I have Nb factorial, they will get cancelled. Right. That's it. There is no other way for Nb atoms to rearrange. When you have Nb sites, they need to rearrange. Right. That's all. It's simple. Right. Or you can just, instead of doing this, you can just arrange a combination process. Combination process is nothing but, if I have Na and Nb sites and I have NT sites, so how many ways I can get arranged? You will get the same thing. Right. So that's it. Now coming to this, how do you relate? So there is a Boltzmann correlation. How do you relate probability to configuration entropy? And one guy did it by a relation, and that relation is called Boltzmann statistic correlation. Log k, or there is in Greek they write it as r log omega, and this omega is configuration, right? So if you do like this, configuration will be equals to nt factorial upon na factorial into b factorial. Now if you substitute that here, it will be r log nt factorial na factorial upon b factorial. Now how do we solve this? Because nt is so large, and even na and b is one mole of Na contains 6.0 to the 10 to the power of 23 atoms. It's a very large number. So how do you solve this? So for that, if we have a very large number, and if you want to find the factorial, there is a correlation, or there is a simplification, which is called as a Stirling simplification or Stirling correlation. So if n is greater than, very much greater than 1, then log n factorial will be n log n minus n. That's it. A simple correlation. So if I do that, it is also called as Stirling approximation. Okay. Now delta S will be equals to r log, sorry, first I have to write nt, right? First we will do this, because ln a by b will be equals to ln a minus ln b, right? So I hope all of you know that. Okay, so nt ln nt minus nt. Okay, so this is one guy. Now again, ln b, ln b1 b2 will be equals to ln b1 plus ln b2. How you people know? Ln a by b will be equals to ln a minus ln b, and ln a into b will be equals to ln a plus ln. These are two simple logarithmic correlations. Now if I do that, then I can take the negative terms outside. So I have n ln a minus na plus nb ln b minus nb. So that will be equals to r. Again, what is nt? Nt is nothing but na plus nb ln nt minus nt. Now I am multiplying minus here with this guy, so it will be na ln na, minus into minus plus, you will have na again minus plus. Let's take these three terms and these three terms as common. Okay, then I have na ln nt minus ln na plus nb ln nt minus here if you take minus common, then NT minus NA plus NB. That's it. So what is NA plus NB? Which is NT. So NT will get cancelled. Then I have R. What is NT minus NA? NT, which is NT by NA, right? And if I take minus common, right? So then this will become ln N NA minus NT plus NB ln NB minus NT. Now what is NA by NT? It is mole fraction of A, and NB by NT is mole fraction of B. Right. Now if I substitute this here, minus R NA ln XA plus NB ln XB. Now we found this is delta S configuration. Now if I am talking per mole, then it will be divided by NT, which is for per mole, delta configuration and per mole. Okay, so NA by NT ln XA plus NB by NT ln XB. So delta S configuration per mole will be equals to minus R XA ln XA plus XB ln XB. That's it. If I have two components, this will be my this, and if I have n number of components, then delta S configuration for a mole will be equals to minus R sigma X I equals to 1 to n x1 xi ln xi. That's it. So if I have 3, then xa ln xa plus xb ln xb plus xc ln c. That's it. Now where was our first correlation? This guy. So this part is done. Okay. Now whenever we are talking about random solutions, then that means there is no change in volume. So if there is no change in volume, then this guy will be 0. Right. And what about this guy? This is change in energy. So whether it is an exothermic or endothermic. Right. If it is an exothermic, then there is a release of energy. Right. And if it is an endothermic, then there is a absorption of energy. That's it. So if for random solutions or for ideal solutions, there is no change in energy. So again, this is 0. So the only term that we are remained with is this guy. Now, so if I do the G2, the final energy, the final energy of the system will be equals to G2 will be what? XA G0 A plus XB G0 B plus RT XA ln XA plus XB ln XB. This is our final correlation. Right. Now, the part is what happens if we want to know what is the so final our goal is to find what is the chemical potential. Right? How do you describe? I mean, how do you quantify it? Right? What is the description? Right? We know the chemical potential is nothing but the change in free energy when you add something into the system. right? When other terms are constant, like pressure and temperature, right? So and that means dou G2 by, let's now talk about only dou N. Okay, then that is, this is the chemical potential of A. Right, then because this is a constant, if this guy is constant, then if you do the differentiation, or let's say I'm doing the differentiation because I'm taking per mole, then this can be taken as dxa, right? Then if this is constant, this will go out, so G naught A, right? Let's not wonder about this one. Okay, let's only do with this guy. Okay, now G naught A plus RT, if I differentiate this guy first, ln XA plus XA, if I differentiate ln X, then it will be 1 by X, so this will be cancelled, it will be 1. Right, now the next one that gets is plus, and because it is an XB, then it is 1 minus XA, right? So again 1 minus XA, 1 will get out, so it will be, this can be written as 1 minus XA GB naught. Okay, so this will be 0, then you have minus 1, so minus GB naught. The same goes for RT, so minus term, RT ln XB minus 1. This guy will get cancelled, so mu A, chemical potential. Whenever there is a change in free energy, right, we have final energy and you differentiate with the dxa, then that will give you the chemical potential. So that will be given as G naught A plus RT ln XA minus G naught B times RT ln XB. So this is my dou G2 upon dou X. Right, and this let's write it again, dou G2 by dou XA equals to G naught A plus RT ln XA minus G naught B plus RT ln XB. So this is our correlation whenever we are trying to do, when we are trying to differentiate our G2 with XA. Okay, so this is how it works. Now coming to the chemical potential part, right? Then if I have dou G see, then how do you write the equation, right? So G dG will be equals to the change in free energy, will be equals to dG upon dNi or dXA or dXi, anything can be taken, right? times dni, then only you will get dg, right? Plus dou g upon dou nj dng. Or you can write it for simplicity, let's write it like this: dou nxa dxa plus dou g upon dou xb dxb. Now if you compare this to this, that's what we did, right? See, now if I do this, what are the things do I have? I have dou g upon dou xa, and because there is an xa, so it will be dou xa upon dou xa, plus you already have dou g upon dou xb, and we have dxb upon dxa. So what does this thing says to you? dxa by dxa 1, so dou g upon dou xa times 1, dou xb by dou xa, so we know xa plus, we are talking about binary, okay, so xa plus xb equals to 1, then dxa plus dxb equals to d1, which is a constant, that will be 0, so dxa equals to minus dxb. And if you substitute here, then it will become minus dxa, dx will again cancel, minus dou g upon dou xb times 1. So let's remove 1, okay? What is this? Chemical potential of VA. What is the change in free energy when you add xa moles of xa moles in AB solution, AB or Y? What is this dGB? A change in free energy whenever you add xb moles of B in a solution. This is chemical potential of B. So dG upon dxa will be equals to chemical potential of A minus chemical potential of B. Now if you compare, let's say this is my equation 6 and here is my equation 5, and you compare 5 to 6, right? See, dg by dxa is same, dg by dxa is same, everything is related to mu A, everything is related to A, B, everything is related to B. Then mu A will be G naught A plus mu naught B this is how chemical potential of atoms is given in an alloy. This is how we derive it, and this is how you measure the chemical potentials of ideal solutions, right? Again, and there is another solution called ordered solutions. In ordered solutions, the change in volume will be 0, but the delta U mix is not equal to 0, and that means the delta H mix, delta U mix plus P delta V mix, this is 0, this is not equal to 0, then delta H mix will be equals to 0. right? Now, how do you define this? So this is for random solutions. So let's start. These are for random solutions. Now what about for this one? This is called ordered solution. In random solutions, we have delta U mix 0. There is no change in bond energy. Right? There is no heat energy release or heat energy absorbed. There is no change in volume. And that's why you have delta H mix 0. But in ordered solutions, that is not the case. Right? Okay. How do we get to this? How do you write this? Right. So I will not derive this part because this part has already derived, right? So sir has derived that quasi-chemical, and this model from which we derived that delta H mix, right? The model that we used is called as a quasi-chemical model. Okay. So there is no quasi-chemical model. Quasi-chemical model is nothing but you just take probabilistic way, right? There is no further interactions. So delta H mix will depend upon the number of bonds being formed, right? So it depends upon PAB. Right? Or I can say first it will depend upon coordination. Each atom, how many bonds it is formed, right? What is the surrounding bonds, right? The surrounding metallic bonds, the coordination of them. Okay, and then we have this guy. Then if I have an atom, what is the probability of finding an atom in any site? It is XA, because number of atoms to total number of atoms, right? Atom applied to total number of atoms, XA. Then what is the probability of finding an XB atom nearby? That is given by XB. Okay. And then you have the energy term. Right. And that is given by EAB minus EAA plus EAB 1/2. It's a simple correlation. There is nothing more complexity there. Right. It is quite simple. And because we are talking about atoms, then it should be multiplied by Avogadro number. So this is our delta H mix correlation. Now, what are the constant terms here? Coordination number is constant, it will not change. The bond energies are constant, they will not change. Avogadro number is a constant, it will not change. So delta H mix will be equals to, so let's envelope all these terms into one term, that is omega times XA into XB. So this is our delta H mix. Now how do we insert this term there? this can be written as, because we need to like differentiate xa and xb, right? So then what you do is, we know xa plus xb equals to 1, so we multiply this to omega times xa times xb into 1 will be 1. Okay. Times 1, which is 1, right, which is again omega xa times xb, but what is 1? 1 will be equals to xa plus xb. Let's write it like this. Then we will have xa square xb plus omega xb square xa. Now let's write this as in one term, okay? So 1 minus xb whole square times xb omega 1 minus xa whole square times xa. Is it attachments? Then g mix will be equals to, what is delta h mix? Omega of 1 minus xb square xb plus 1 minus xa square xa plus xa rt ln xa plus xb rt ln xb. So we know delta g mix will be equals to xa mu a plus xb mu b, right, from here. See? So what is, if I take xa terms common, then xa will be equals to, what are the xa terms? This guy, I have this guy and this guy, so it will be rt ln xa plus omega 1 minus xa whole square. This is chemical potential of A. What is the chemical potential of B? Is mole fraction of B times RT ln XB, this guy, plus omega 1 minus XB whole square. So this is for regular solutions. So far we have discussed two terms. One is your, what do we call, random solutions, and the second is for regular order solutions. So it is not regular. Okay. Now, how do we apply these things? See, chemical potentials. Now the main part comes. That is the application of thermodynamics on nanomaterials. Now, how to use whatever the thermodynamics part we have learned in nanomaterials, right? Now, first, let's see how do we apply this to whenever you have, So then the first thing we will do is, suppose I have a bulk particle, and it is a bulk, and it has 10 micrometers of radius. Now I have another particle, nanoparticle, which has 50 nanometers. Now let's say this is my face, so I'm solidifying this thing here. It is moving down. So this thing is moving, so I'm cooling it, right? So this part. Let's say I'm cooling this alloy here. Okay. So how the composition will change? So for bulk, it will be simple. It will be very simple. The composition will go down like this. Right. So here I have alpha. Here I have liquid or beta. So my alpha composition will move like this. Whenever I go down with temperature, the composition alpha will change like this. This is my trend. Okay. So whenever my temperature goes down, the alpha composition will take this black part for bulk. Now what about for nanoparticle? Will it be the same or will it be different? Right? Now let's see. Let's see how it is same or different. Okay. Free energy of alpha will be equals to, let me the alpha phase. This is same the alpha phase. That's right. So how my composition will change? The composition of alpha. Right. So whatever we draw a good curve. So this phase. This is T1, T2, T3, T4. At T1, the composition is x1 of alpha. This is my alpha. Let's keep it right. Okay. So at T2, the composition of alpha is x2. At T3, the composition of alpha is x3. And at T4, the composition of alpha is x4. So my composition is decreasing. So let's write the trend. x4 is less than x3. Yeah, x4 is less than x3 is less than x2 is less than x1. Now coming back to the part. So we have defined our compositions. So my composition is fixed. It will be from here to here. It will follow this path for bulk particle. Will it be same for nanoparticle? Let's see. So let's write free energy of alpha will be equals to free energy of volumetric alpha plus free energy coming from surface. The volumetric free energy plus the surface energy. Right. Now what I'm trying to do is I'm trying to differentiate it. Let's do rho J alpha upon rho n. Right. So this will be equals to volumetric factor is let's say our surface energy is constant. Let's say our surface energy is not changing much. Okay. Then I have dou A by dou MA. Now let's take, because we are taking a sphere, so it has an area of 4 pi r square. Right. Now if I do dou A by dou r, let's do it later. Okay. So dou A by dou r equals to 8 by r dr. Right. Now there is another term called n. We have to remove n. Then how do we remove that? We know how the number of atoms will change our radius. Right. And it happens d by dr upon 4 by 3 pi r cube divided by volume of each atom. Right. So that's how you change. For example, if you have 20 atoms, then it has certain volume, and if you add 5 atoms, then its volume will change. That means the radius will change. So this is how you give the correlation, and this will be equals to dou n A by dou r will be equals to dn by dou r will be equals to 4 pi r square upon v atomic volume. And there is also the dr. Right. Now what I'm trying to do is I'm trying to multiply 1 and 2. So multiply 1 and 2. What this will give me? This will give me dA upon dr into, no, let's multiply, let's reverse this and then we multiply. Then it will be dr upon dNA, and that will be equals to 8 pi r dr into v atomic volume upon 4 pi r square dr. And according to the chain rule, it will be dA upon dN. 4 times 2 is 5 pi r dr. So 2 v atomic upon r. If I multiply with surface energy, it will be like this. Right. Now let's put that on there. What is that? Here. Now what is dou G upon dou NA, which is the chemical potential. First, let's write the equation first. Okay, so dou G alpha upon dou NA times the volumetric free energy plus gamma dA upon dN. Simple, right? Now what I'm trying to do is I'll substitute this guy here. Okay, so dou G alpha volumetric plus gamma 2 gamma v atomic volume divided by r. Now what is my volumetric free energy? We are only considering volume, there is no surface. Then this will be equals to RT XA G0 A plus RT XA from XA. I'm talking about only alpha, then there will be no XC. Because we're talking about per mole. The volumetric frames, yeah, you will have an XC and XC. Right, that's it. So what do we have here? Okay, so let's not just give an alpha here. Let's first do that. Let's not confuse things, okay? Let's put alpha here, okay? Then if I'm only talking about G alpha, this will be my XA. So you will not have this, because we are talking about one mole, right? We are talking about one mole. So this is my thing. Then mu A minus this guy, volumetric free energy of alpha will be equals to RT, sorry, XA upon RT ln XA. Right, the volumetric free energy, only the term come not, there is nothing else. So that's why this will be equals to XA RT ln XA. That's what we derived, right? Mu A will be equals to GA plus XA G naught A RT ln XA RT ln XA. That's what we derived. Right, so you will get RT ln XA. It is upon R. We are discussing for R. Let's write it again, because it is, you will get confused. So up to this it's okay, right? There was no confusion. Now this term is equal to chemical potential. This is for volumetric free energy. Then if I am telling about volumetric free energy, what do I mean? So volumetric free energy can be written as, so G naught A plus mu A, G naught A XA ln XA. This is the volumetric free energy of G naught. Okay, so you have another XA, and then you have, because that is what we learned, right? So G total will be equals to GA plus GB, or alpha plus beta. That's it. Now plus 2 gamma V upon it by R. Mu A is for particular R. Okay, and this is for volumetric term. That means there is a very big volume. That means the R equals to infinity. Okay, so I guess again I made a mistake. See, why I was doing mistake was I was confusing with what do you call it? R equals to infinity. See, at first we have derived this part. Is it? Yeah, this is the actual term. XA times Z naught A plus XP times Z naught A. See, this is how it should be. So we need to understand what we have, what we are taking, right? So if I am writing like this, G total will be equals to NA XA, sorry, NA GA plus NB GB. Now what is GA? GA is a free energy per mole. Right. Now what is NB? NB is free energy per mole of B per mole. Now what is GT? GT total free energy. This is not per mole. Right. Because of total free energy, we need to divide it by NT. Right. Then this will be per mole GT dash NA by NT GA plus NB by NT GB. That will be equals to XA GA plus XB. See, that's the simple confusion has made a lot of mistakes here, right? So it should be like this. We have to be very clear with what we are defining. Even if we do a single mistake, so that's what we did here. That's why it took us so long to complete this derivation. Now, this is for R equals to infinite because we are talking about only volumetric energy. Volumetric energy term, it is purely focusing on volume part. There is no surface area. That means it is very big. That means R is infinite. Now coming to R, this is for particular R, right? Chemical potential. If you have a sphere R, if I add 4 atoms into this 50 nanometer sphere, then what is my free energy? So that is what this guy tells me, right? Then mu A can be written as G naught A plus ln XA at R equals to R equals to G naught A plus ln XA at R equals to infinite plus 2 V atomic by R. Right. Everything we are writing it for alpha. There is no involvement of or any other fields. Okay. Let's have one more slide. So let's write here itself. Okay. So then we have G naught A at R equals to R minus G naught A at R equals to infinite. This is one term plus RT ln XA at R equals to R minus RT ln XA at R equals to infinite. Which will be equals to 2 gamma atomic volume. Again, let's give any random variable to it. Because we know what it is, right? Divided by R. This is the free energy, surface free energy, and this is the radius. Now, for pure, everything will be constant. Just like I have said here. If everything is pure, then it's just simple addition. If something is not pure, it's like mixing two things, ethanol and water, there is an interaction. Then it will not be a straightforward. Right? If everything is pure, it's just a simple algebraic expression. Just add things. That's all. Right. So for pure, everything is same. So G naught A and G naught A will be cancelled out. Right? This will be 0. Then the remaining term is RT ln, again ln A minus ln B ln A. T ln x at R XA at R equals to R XA at R equals to infinite times 2 gamma atomic volume times R. RT comes here, so we have R and T. So XA R equals to R, XA R equals to infinite times exponential cases. For bulk particles, R is large. Right. So if R is large, then what happens? This term is very large, and this term will go down. Oh, sorry. If this term will go down, right? And we know for exponential of x is equals to, which can be approximately equals to 1 minus x. If x is very small, right? This is 1 minus x. If x is tending, if x is 1 by infinite, right? X, what is x here? 1 by 1 minus r. If r is tending to infinite, then what is this term? It will be 0. That means if r is very large, then this term doesn't have any effect, right? If this term doesn't have any effect, then r equals to r, then this term will be equals to 1. So that will be approximately equals to, say, r equals to infinite. So the composition will follow a simple path, just like here. But what happens if my r is small? Second case, for nanoparticles, r is small, then what happens? Then xa r equals to r, xa r equals to infinite, then you have a dominating term here. Why? Because if r is getting decreased, then this term will increase, and that means this 1 minus 2 gamma RTR, this value will go up, so not 0, so this value will rise, then 1 minus x will be a negative number, sorry, not 1 minus x, it will be a small number, right? Then our xa will go down. That means our mole fraction or the composition will change. So that is the effect. Now for bulk particles, xa r equals to r will be equals to, say, r equals to infinite times 1 minus 2 gamma atomic volume upon RT times the function of r. Right, so that's how the variation takes place. Variation of atomic radius, the variation of nanoparticle radius with respect to the composition. With composition. next part of the application of thermodynamics on nanoparticles is how the nanoparticle size will change with temperature. Nanoparticle size will affect its melting point. Let's take this is my nanoparticle and inside is an alpha and my wafer phase is defined as a beta. So moving on to free energy equation, V alpha dt, V alpha dt minus S alpha dt, and dg beta will be equals to V beta dp minus S beta dt. At equilibrium, we know the interface pressure. Pressure variation. But there are many terms: interface pressure, pressure variation, and excess pressure. Is P2, which is the pressure from outside, or sorry, inside, will be equals to P1 plus 2 gamma upon C upon R. So that's why I have given relation for curvature. So curvature is given by constant upon R. So it depends upon time. So if it is a sphere, then it will have a 2 by R. Right. So if you have a more three-dimensional curvature, then it will be C1 plus C2 upon R. Or you can take C1 upon R1 plus C2 upon R2. This will be another type of curvature, or the concave curvature in 3 dimensions. Differentiation. At equilibrium, you have dg alpha equals to dg beta, V alpha dp minus S alpha dt, which will be V beta dp minus S beta dt. Right. V alpha minus V beta dp equals to minus of S beta minus S alpha dt. Right. Now P2 is nothing but P beta and P1 is nothing but P alpha plus 2 gamma C1 R. This will be equals to temperature is same along the interface. Then V alpha times so this is alpha, this is beta. Okay, this is V alpha, V beta. So beta. Okay. Then you can just state this will be written as, you have to differentiate this now. So dp alpha equals to dp beta plus 2 gamma c1 of r square dr. We will have minus sign. So from substitution, it will be dp beta minus b alpha 2 gamma c1 upon r square dr minus b beta db beta minus delta s dt. So v alpha minus v beta dp beta minus v alpha 2 v alpha gamma c1 upon r square dr delta s. Now, and we know vapor pressure is very much larger than V alpha, so this will be approximately equals to minus V beta. Right. Now if I write everything in terms of temperature, so we have V alpha minus V beta, and then I have dp beta. So dp beta will be dp equals to RT, then dp by dp equals to E equals to RT by dp equals to 1 by E square dv. And that will be equals to RT by E square dv. It's cancelled. There is a change in temperature, right? So we can write in terms of temperature. And this will be equals to, so dT upon T then 2 V alpha gamma c1 square delta H. And we have dr. So this will be ln T upon T for particular temperature, and this is T for bulk temperature. It's melting. Okay. And then you have all the things here. C1 H times dr upon r square. Right. Or we know the volume of alpha. Volume of alpha will be 4 by 3. Let's write it here. 28 by 3 gamma C1 100 minus 1. This is also 5. R cube R square will be R dr. And then we have the R square vector. R square is to 4. Then Tm R equals to Tm melting times exponential 1 minus. So we will get some constant upon. So this is how the melting point will change. This is how 1 minus and approximate, right? This will be 1 by some constant upon 1 by r. That's it. So if the radius of a nanoparticle decreases, then the melting point will also decrease. Because this R, and this R goes down, this term will increase. Right? That's it. The melting point will decrease. I'll stop right here. What is 1 by exponential from this particular this. This will be equals to 1 minus 1 by constant by r. So now radius decreases and this term will increase. Right. 1 minus this term is less than 1. So this term will decrease. Increase, then this term will go down. And if this r tends to infinite, then 1 by r will be 0. So for bulk, Tm r will be